Welcome. The next topic that we are going to see is normal distribution. But before going to the normal distribution, here I have shown some image, some bell curve, isn't it? Okay. This is going to illustrate the situation where we make use of normal distributions. Okay. So usually our entire stuff, okay, in life is going to model through this bell curve or yeah, mostly it is going to happen. 50 percentage of the things will meet the expectations, whereas 15 percentage will be either above expectations or below expectations, whereas on either side 10 percentage is seriously underperformance or excellent performance. Either they'll be super good or super bad. Okay, so here and all in these situations and all, we are not very sure of the distribution that it is happening. Whereas this normal distribution is also having a bell-shaped curve as that of it. That is why for most of the real life problems that we deal, if we are unable to identify some suitable distribution for it, we just assume that it is following normal distribution. Okay, and here if you see in this graph I have shown you something, I have shown you different graphs which are normal distribution curves. Okay, so the first one, as the color indicates, you are able to see this blue, red and yellow or orange. This curve has mu value 0. So this is the point of symmetry. Okay, so this is the average performance of the people or the items that is considered. Okay, whereas in the green one, this is the average itself is -2. So this has a bell shape about this -2, whereas other three has a bell shape about 0. Okay, based on the variance value, that is sigma square is the usual sigma square, that is variance. Based on the variance value, if the variance is large enough, the curve has a very small peak. Okay, if the variance is very small enough, the curve has a very larger peak. Okay, so now that if you try to plot the density function of a normal distribution, that is how you would get some graph. As in the previous distributions, to describe a particular distribution, we need a set of parameters. For all the discrete distributions, I have specified the set of parameters that are required, whereas for uniform distribution, we need the maximum and minimum value, that is a and b, right? So if we know the interval, that is more than enough to describe the uniform distribution, whereas a normal distribution we need to know the mean and variance. Okay, why? Because here we are dealing some real-time situations where we don't know the type of the distribution that the population or the group is following. Okay, so we expect some average value, that is what is mean is, and we say that to a certain extent we accept the variance. Okay, if you come here, like even if they come to this level, okay, that is if they are too worse, that is their performance is 0, from 0 to 10, we do not accept it at all. Okay, from 20 it is okay. So if this is the average thing, from here to here we are accepting nearly 40 percentage is accepted. Okay, so this variance we fix it up. Based on that variance and the mean, we are defining the density as in this form. Okay, so here if you plot it as shown in the graph, it has a bell shaped curve which is symmetric about the line x equals mu. Okay, now we will try to derive the MGF of this one. Okay, now that we know the mean and variance, but still we will try to derive the MGF. Okay, here our density function is what? It is 1 upon under root 2 pi multiplied with sigma. Sigma is outside the under root, and exponential of minus 1 upon 2 x minus mu upon sigma whole square, right? And we know that m of t, that is moment generating function, is expectation of e to the power tx, which is nothing but minus infinity to infinity. Yeah, this is one speciality that I failed to tell you guys. Here we are defining this one in the interval minus infinity to infinity. As said, whenever we do not know the type of the distribution that the set of values is following, we consider this one. So we accept extremes in both the directions. That is why it is defined from minus infinity to infinity, right? Okay, coming back to the derivation of moment generating function, it can be now written as e to the power tx multiplied with 1 upon under root 2 pi multiplied with sigma exponential of this e and exponential both mean the same. Okay, 1 upon 2 x minus mu upon sigma the whole square dx, isn't it? Now I am performing some change of variable. Okay, so let me take z to be x minus mu upon sigma. So then what happens to my x? It is z sigma, right, plus mu. Now my dx is what? Sigma times of dz, right? Now substitute, and my x is varying from minus infinity to infinity. In that case, my z is also going to vary from minus infinity to infinity. Now coming back to this m of t, it is okay. Now let us try to take out the constants which are present inside it. This 1 upon sigma times of under root 2 pi is a constant, so we take it outside. Integral minus infinity to infinity e to the power t times of z sigma plus mu multiplied with exponential of minus half times of z square multiplied with what? Sigma times of dz. The sigma is again a constant, so we take that outside. Okay, upon sigma times of under root 2 pi. And if you notice here, z is the variable upon which we are integrating. So this mu has nothing to do with z. It is independent of z. So we can take that quantity also outside. E to the power t mu. We take it outside. So now it is from minus infinity to infinity. E to the power t z sigma. Again, now we have it in a simplified form. So let me just write it as simply e to the power minus half times of z square and dz. Sigma and sigma gets cancelled. So what I have is 1 upon under root 2 pi. Okay, e to the power t mu. And now this one, let me write it as exponential of minus half times of z square. I have taken this minus half outside. Okay, basically what happens here is that this is exponential of t z sigma minus z square upon 2. Okay, we have something of this form. From here, this is what? M of t, isn't it? M of t equals 1 upon under root 2 pi e to the power t mu integral minus infinity to infinity exponential of, let me take this minus half outside so that it is z square, and we just have to multiply and divide it by 2, and we have taken minus half outside, so it is minus times of 2t z sigma, it is with dz. Now we know that a plus b, okay, a minus b whole square is a square minus 2ab plus b square. Okay, taking a equals z and minus 2ab equals minus 2tz sigma. Okay, then we know a 2 is 2, minus is minus itself, so this tells us b is t sigma, isn't it? So we just add this t square sigma square and minus t square sigma square here. So our m of t becomes 1 upon under root 2 pi e to the power t mu. It is from minus infinity to infinity exponential of minus half times of z square minus 2tz sigma plus t square sigma square. Okay, that minus t square sigma square along with this one, that one we write separately since it is independent of z. So that becomes what? Here we have minus, again here we have minus, so it is simply t square sigma square upon 2 and dz. Now it is again independent of z, so we take that also outside. So it is 1 upon under root 2 pi e to the power t mu plus t square sigma square upon 2 from minus infinity to infinity exponential of minus half times of z minus t sigma whole square dz. Now we are going to make some observation. Coming back to the density of this one. Okay, now here what we are going to do is that if we have to say x is a normal random variable with mean mu and sigma square, then it should have this density function, or if it is having this density function, then we can say x is a normal random variable. Now letting sigma square equals 1. Okay, so what happens here? It will be f of x equals 1 upon under root 2 pi e to the power minus half times of x minus mu whole square. Okay, where mu is the mean of this thing. Now, when sigma square is 1, this is going to happen. Okay, keeping that in mind, come back here. Okay, here we let us do some rearrangements. Okay, when we do some rearrangement, it is e to the power t mu plus t square sigma square upon 2. This one we will write separately. 1 upon under root 2 pi minus infinity to infinity exponential of, that is e to the power of minus half times of z minus t sigma whole square dz. Isn't it? Here this x was just a variable which is ranging from minus infinity to infinity. Whereas here also we have z which is ranging from minus infinity to infinity. Okay, in the place of mu, what we have? We have t sigma. So here we have everything in terms of z. So we can say that this z is a normal random variable with mean t sigma and variance 1. So whatever we have here is the density function of it, and which is integrated from minus infinity to infinity. Therefore 1 up in 1 upon under root 2 pi. Okay, you can take it inside as well, there is a no harm. Minus infinity to infinity exponential of minus half times of z minus t sigma whole square dz. This should be 1 since it is the density function over this limit. So this is telling us what? This is telling us that moment generating function of any normal random variable. Here this is the mgf of, just a minute, let me use other color. So mgf of x, which is following normal distribution with mu and sigma square. Okay, so this is exponential of, that is e to the power of t mu plus t square sigma square upon 2. This is the MGF. Coming back to this slide, we have the same, right? So that's it for this video. We will continue the discussion on normal distribution in the next video as well.